Greetings, everyone, and I believe you are well in this afternoon. Welcome to the session for tonight for Physical Science, grade 11. I want to take you through the quantitative aspects of chemical change. Let me share the slides. Right, so this is the slides for the quantitative aspects of chemical change. And I strongly believe that you will enjoy the session. We can now start. Okay, let me try to. Okay, first of all, let me share it here. Right. Now we can start. We can start, guys. Okay. Okay, now this is the question. Let me try to zoom in again. The first one, it says, from the quantitative aspect of chemical change, we're going to start on question 5. Question 5, it says, it reads thus: aspirin is known by the chemical name, which is acetylsalicylic acid. So no, this acetylic salicylic acid, it is generally known as an aspirin. Now, we are told that the empirical formula for an aspirin consists of 60% of carbon, 60% of carbon, and the 44.44% of hydrogen and an unknown percentage of oxygen. So now from this, you can easily see that we're given percentage of carbon and we're given percentage of hydrogen, which means we can get the percentage of oxygen because this must have 20%. So the first question says, define the term empirical formula. Empirical formula is the simplest whole number ratio, of atom in a compound. The simplest whole number ratio of atoms of elements in a compound is called the empirical formula. And the second question says, determine the empirical formula of this aspirin. So we want actually to determine the empirical formula of aspirin. So now, to determine the empirical formula, we need to know the mass of each atom, of each element. And from the mass, we need to determine the number of mole, and we get the ratio of each element in terms of the number of atoms. So what we're going to do is we're going to construct our table. So here we have carbon, hydrogen, and oxygen. Within this, we are actually given the percentage of each element. So with that percentage of each element, we assume that 60% is actually the 60 grams of carbon from a total of 100 grams. If we are comparing with it, like from a total of 100 grams, it means carbon will be 60 grams of carbon from a total of 100. And hydrogen will be 4.44 from a total of 100, which means that from that percentage, we can get the percentage of oxygen. And the percentage of oxygen will be 100 minus 60 minus 4.44, which means Oxygen has a percentage of 35.56%. So it means now in each element, we have to first determine the mass. Already the mass of each element is already provided. The carbon has a mass of 60. So it's 60 grams from a total of 100. The hydrogen will be 4.44. Oxygen will be 35.56. Now, with this, we have to determine the number of mole of each element, 0.56. To determine the number of mole is mass over the molar mass. So we have to use the formula of mass over the molar mass then in order to get the ratio. So now what we're going to do, we have to use the periodic table in order to get the molar mass of each element. So now from here, okay, let me just try to extend this table, guys, okay. Right, then what we're gonna do is we'll have to, let me try to construct this table. So now what we're gonna do is we have to calculate the number of mole of each. So the number of mole here will be, for carbon, it will be the mass, it's 60. Then the molar mass of carbon is 12. Same applies, the mass of hydrogen is 4.44. The molar mass is 1. And the mass of oxygen is 35.56. Then the molar mass is 16 from the predicted. So now we can determine the number of mole of each. So here we're going to have 60 divided by 12. 60 divided by 12 is going to give us 5 mole. Then 4.44 divided by 1 is 4.44 mole. Whereas 35.56 divided by 16 is 2. Let's round to 2 decimal places, 2.22. Now from here, we have to determine our ratio, the ratio. Now to determine the ratio here, we are going to divide the number of mole by the smallest number here. Obvious, which one is the smallest number here? The smallest number is 2.22. So it means we're going to say 5 divided by 2.22. Then 4.44 divided by 2.22. Followed by 2.22 divided by 2.22. And this one will give us a ratio of 1. And this one will give us a ratio of 2. But here, when we say 5 divided by 2.22, the value is giving us 2.25. And when we look at this, if we have to simplify this to the nearest, this will actually give us 2. But having looked, if we to check on this, here we got 4.44 divided by 2.22, which just gives us a whole number of 2 and a whole number of 1. Which means here we need to be careful. We cannot say this as a whole number of 2. Why? Because already this one is giving us 2, which means this is roughly 2.2555. So if we calculate that using a calculator, 2.25 is the same as 9/4. So it means if it's 9/4, it means it shows that we need to rewrite this again. So okay, fine. Since now we have 9/4 and we want to simplify this to the nearest, it means we have to get rid of this fraction. So to do that, we need to multiply everything by 4. This will have a whole number ratio of 9. This will be 8, and this one will be 4. So which means that the empirical formula of aspirin is C9H8, then O4. Okay, so this is what we got. Reason being, we do not want to write, we cannot round this to the nearest. Reason being, already this is the nearest whole number, and this one is the nearest. So it means this one shows that it's actually 2 point something. It's already above 2. But in terms of the rounding, we're supposed to say to the nearest whole number is supposed to be 2, but because of already this we got 2, it means this one we need to actually write it in the form of a fraction. So this is the empirical formula of aspirin. Then the next question says, if the molecular formula of an aspirin, the molecular mass of an aspirin is 180 grams per mole, what is actually the molecular formula? Remember, this is the empirical. Now we want to get the molecular formula of aspirin. So do that. We are already given the molar mass of aspirin. And what we can do is we have to calculate the molar mass of the empirical formula of an aspirin. So it's C9H8O4. So which will be 9 by 12 plus 8 by 1 plus 4 by 16. And what is the molecular mass of the empirical formula of aspirin? It's 9 multiplied by 12 plus 8 multiplied by 1 plus 4 multiplied by 16. So this gives us the molecular mass of 180 grams per mole. This is for an aspirin. So what does it mean? It means that in terms of the ratio, so we're going to say our ratio here, we're going to take the molecular mass of the aspirin, the actual one, which is 180, then we divide by the molecular mass of the empirical, which is 180, which means there's a whole number of 1, a ratio of 1. So if it says a ratio of 1 means you have to multiply everything by 1 here. It means the molecular mass of this aspirin, I'm going to say molecular formula of an aspirin, it's C9H8O4. So this is the molecular formula of an aspirin, of this aspirin. Okay, just a minute. I wanted to check something, but I believe this is the correct answer. Okay, I wanted to check something here. Let me just go to Google, just a minute. Okay, let me stop sharing for now. Okay, let me just go to Google. Okay. I want to check something. Okay. I should have went through the screen. Okay. Okay, just a minute, guys. Okay, I actually want to check the actual molecular mass of this acetylsalicylic acid, but I believe that is the correct answer. Okay, fine. Let's move on. You can also confirm. I want to check through internet, but it's fine. I'm failing to go to Google here. Okay. Google Drive, Microsoft Share. Okay, it's okay. Then we can just continue. Can continue. Let's continue. It's okay. It's fine. Let me check something. Oh, this is the. Okay, let me try. Oh, okay. Now I see. I see it now, guys. Let me just want to add something. Okay, salicylic acid. Yes, it's C9H8O4. So this is the correct one. Okay, this is the molecular formula of salicylic acid. So it means everything's right. Right now, let's continue. Let us continue, guys. I apologize for the delay. Right, then next question, when we're going to move on to the next one, then it says, The molar mass of hydrated sodium carbonate is found to be 268 grams per mole. So it means here it is sodium carbonate that is with water actually. The hydrated sodium carbonate has a molar mass of 268 grams per mole. But now we are told that the formula for the hydrated sodium carbonate is this one. So it means it is the sodium carbonate that is actually having water in it. Right now, this has a molar mass of 268. And the question says calculate the number of mole of water, which is X. We actually want to know what is this X here. Of water in a compound, in this compound. So we want to actually know what is the mole of water in this hydrated sodium carbonate. So to do that, what you can do is actually we can do, okay, fine. We are given that this has a molar mass of 268. So it means if we know, for example, if we know the molar mass of this sodium carbonate without the water component, then what we can do, we can be able to know the molar mass of this. So what we can do is let's calculate the molar mass of just sodium carbonate. So the molar mass of sodium carbonate is 2 times, for sodium is 23 from the periodic table, plus carbon is 12, plus 3 multiplied by 16. Because we have 2 atoms of sodium, 1 atom of carbon, and 3 atoms of oxygen. I believe you understand how I got the answer. Right. I got the answer from actually, you see from our periodic table, sodium has the relative atomic mass of 23, that is. Carbon has 12, the relative atomic mass of 12, that is there. Then oxygen is 16. So I believe you are following. So let's go back and compute our question. So this will give us the molar mass. The molar mass of sodium carbonate would be 2 multiplied by 23 plus 12 multiplied by, 12 plus 3 into 16. This gives us 106 grams per mole. And sorry, it's 106 grams per mole. So what does this mean? It means that from the hydrated sodium carbonate, this one has a molar mass of 268. And if this one has a molar mass of 268 grams, we know the molar mass of sodium carbonate is 106. It means we can know the molar mass of this water. Right, so we're going to have, with the X mole of water, we know now we want to get the molar mass of this. And to get the molar mass of this, it means from 268 grams, we're going to only subtract 106 for sodium carbonate. So it means this one will give us 268 minus 106. This one will give us the molar mass of 162 grams. So the 162 grams, it is the molar mass of water together with the number of mole of that water. But now with this, since we want X, we can say, okay, fine. We can know the molar mass of water only. What will be the molar mass of water? The molar mass of water, it will be 2 multiplied by 1 plus oxygen is 16. And this will give us 18 grams per mole. So what does this mean? It means now we are comparing X mole of water and also with the 1 mole of water. Because this one, if we had this one has a 1 mole of, like it has 1 mole. So it means now we are using X is to 1. So we wanted to know what is this X. But now, what is the molar mass of water with the X? It's 162. And what is the molar mass of water? It's 18 with a mole of 1. So it means now we can determine this x. We can cross multiply here, and this will be 18x equals to 162. Then it means we divide everything by 18. We divide everything by 18. So this one will have how many moles? It will produce, it will give us 9 moles. So it shows that this value of x is actually 9. I believe you are following. I believe you are following, guys. Okay, I just want to check something. And to confirm that, what you can do, you can, where there is x, we can substitute this by 9 to confirm if. So it means the dehydrated water, dehydrated sodium carbonate will be like this. So let's calculate the molar mass of this. So it means we know the molar mass of this one. We've calculated it's how much? It's 106. If we take 106, we're gonna have plus 9 multiplied by the molar mass of water, it's 18. So you see that we're going to have 106 plus 9 into 18. Then it will give us the molar mass of 268 grams per mole. I believe you are following, guys. I believe you are following. So it means the value of x there, the number of mole of water, it's 9. Right, then we're going to move on. We're going to move on. Please, if you don't understand, just pause the video and go through it step by step. Then you'll understand what I've actually done here. Right, let's move on to the next question. Without wasting time, let's move on to the next question. So we're going to address quantitative aspect of chemical change. Then after break, we'll look at the acid and base. Now, question 6. Question 6. It says, if a solution of silver nitrate is mixed with a solution of potassium chloride, a precipitate of silver chloride is produced to the following reaction. What do we mean by a precipitate? A precipitate is just a solid substance formed in a reaction. A solid substance formed in a reaction. It's actually called a precipitate. Now, from this reaction, we are told that they reacted potassium chloride and silver nitrate to produce silver chloride and potassium nitrate. And I strongly believe you know how they got the product. Remember, we can use the ionic reaction, the plus and the minus. Here we put positive ion, here we put negative ion. Potassium, it is in group 1, so it will have a positive charge. So it will be plus, then chlorine will be minus because sum of charges must be 0. Silver, it's plus, ion, it's a positive ion, then nitrate, it's a negative ion. Then they've cross multiplied. That's why they got this. So I believe you are following. Then now, from here, what we can do is we can just go through the question. It says 55 centimeter cubic. 55 centimeter cubic. This is the volume of potassium chloride. This is the volume of potassium chloride with concentration of 0.25 mole per decimeter cubic. We know concentration is the number of mole of solutes per unit volume of a solvent. So this is the formula for calculating the concentration. So this is the concentration of potassium chloride, and it's added to a volume of 70 centimeter cubic. this volume as 70 centimeter cubic of silver nitrate solution with a concentration of 0.15. So we are given the concentration of the two substances. Right, then the question says, what is meant by a limiting reactant, a reagent? A limiting reagent is a reagent or a reactant that is used up, a reactant that is used up completely in a reaction. A reagent that is used up completely in a reaction or in a chemical reaction is called a limiting reagent. Substance that is used up completely in a chemical reaction is called a limiting, which means the one that is not used up will be the excess. So what does this mean? It means this is a substance that will actually be like, that will determine whether the reaction is stopped or not. So if the reaction stopped, it shows that the limiting reactant is no longer there. It's used up in the reaction. So that is the limiting reactant. Then the second question says, which substance is the limiting? So we wanted to know between potassium chloride and silver nitrate, which of the two is in excess. I'm going to say it is the limiting. So to determine the substance that is the limiting means we need to compare in terms of the number of mole. All right, let us go through the question together. So what we're going to do is we have to calculate the number of mole of potassium, the potassium chloride and silver nitrate. Then we compare in terms of number of moles. So what we're going to do, we're going to sort of find. Let's start with potassium, sorry, I apologize. Potassium chloride. What are we given on potassium chloride? Potassium chloride has a concentration of 0.25 mole per decimeter cubic, and the volume, which is 55 centimeter cubic. We need to convert this into decimeter cubic. We divide by 1,000. So this will be 55 divided by 1,000. It's 0.055 decimeter cubic. Why are we dividing by 1,000? Is because 1 decimeter cubic is equals to 1,000 centimeter cubic. So converting from this to that means now we have to divide this by 1,000, because if you put 55 there and there it will be x. So cross multiplication then will cause this to divide by 1,000. So now we can calculate the number of mole of potassium nitrate. And to do that, we're going to say concentration is the number of mole over volume. Then make number of mole subject of the formula N equals to CV. Then the C will be 0.25 multiplied by 0.55. And this will give us the number of mole of 0.25. And this will give us the number of mole of 0.0138 mole. Let's round to 4 decimal places. So it means initially, the initial number of mole of potassium chloride is 0.0138 mole, 38 moles. Now we're going to calculate that one for silver nitrate. We do the same. We're given the concentration of silver nitrate is 0.15 mole per decimeter cubic, and we're given the volume. The volume is 70 centimeter cubic divided by 1,000. So 70 divided by 1,000, and this will give us 0.07 decimeter cubic. So concentration is number of mole over volume, which means number of mole will be concentration times volume. Concentration is given as 0.15. The volume is 0.07. And now we're going to calculate the number of mole. So the number of mole for silver nitrate will be 0.0105 mole. We want to know which one it is in excess and which one will be the limiting. So to do that, we will go to our reactions. Okay, by looking at the reaction, this one has a mole ratio of 1 and this one has a mole ratio of 1. What does it mean? It means 1 mole of potassium chloride will react with 1 mole of silver nitrate up to the reaction. And what does this mean? It means if we were to compare potassium chloride and silver nitrate, we'll say in terms of ratio, it will have 1:1. And now ask yourself, if 0. Let's assume potassium chloride used 0.0138 mole. If potassium chloride uses 0.0138 mole, it means even silver nitrate will require 0.0138 moles. So if potassium chloride uses 0.0138 moles, even this one will need 0.0138. But now look at this. This one, silver nitrate, if the two has to react with this ratio of 0.0138 and 0.0138, potassium chloride will use that moles, but now silver nitrate has how many moles? Has 0.0105, which is less than the 0.0, which means that it will not be possible for potassium chloride to use 0.0138 with silver nitrate, because it has 0.015, which is less than what is expected. You see that it will not be possible. What does this mean? It means that for this reaction to take place, it means that silver nitrate is the one that must use 0.0105 mole, whereas even potassium chloride has to use that 0.0105. So what does it mean? It means that if silver nitrate uses 0.015 moles, whereas potassium chloride will also use that 0.015. What does this mean? It means that if silver nitrate uses its moles, it means it's going to be used up. And how about the potassium chloride? Potassium chloride, if it uses 0.015, it will still have an extra number of moles that will be left. Because now, if from its initial, it had 0.0138 mole, but from 0.013, it will use only 0.0105. So it means from its mole, it will have an excess of 0.0138 minus what it has used, 0.0105. You see that will have excess number of electrons, the number of moles. So 0.0138 minus 0.0105. So it will have an excess number of mole of 3 multiplied by 3.3 times. So it means, what does this mean? It means potassium chloride will be in excess. It means it will not react completely. So what does it mean? It means silver nitrate is the limiting reactant. Why? It will use all its moles. So if it uses 0.015, this will require 0.015. It means this one will no longer have the number of moles because it will use all of them. So it means from 0.015, the potassium chloride will still have excess of 0.0138 minus 0.015. So it means silver nitrate, it is in excess. Okay, silver nitrate. No, silver nitrate is the limiting, I apologize. So it is the one that will be used up. Since it's the one that will be used up, it means it's the one that will consume all its number of moles. Whereas potassium chloride will only use 0.015, but it will still have excess of 3.3 times 10 to the power minus 3. Which I believe is the same as 0.0033. Yes, 0.0033. 0.0033. So it will have excess of 0.0033 mole. I believe you understand. I believe you understand. Now the second question says, what mass of silver chloride has precipitated? We want to know the mass of silver chloride. And to do that, what we're going to do, we're going to say, okay, fine. Let me try to erase some of the things here. Okay, now we know which of the substance is limiting. It's silver nitrate. So it means since we know that silver nitrate has reacted completely, is the one that we'll have to use to compare it with silver chloride. Because it means that silver nitrate is used up completely to produce silver nitrate. So it means from our calculation, we can compare silver nitrate with silver chloride. Why? Because silver nitrate is used up completely. We want to answer this question. So we're going to say, okay, fine. Silver nitrate is the limiting. Now we are comparing it with silver chloride. So what is the mole ratio? 1 mole of silver nitrate will produce 1 mole of silver chloride because our reaction is balanced. So we're going to have 1:1. So what does this mean? It means if silver nitrate uses 0.0105 mole, it means this will still have the same. Even if cross multiply, it will still have 0.0105 mole. So now we are comparing silver nitrate and silver chloride. 1:1. Now we know the number of moles of silver chloride. It means we can calculate the mass of silver chloride. I believe you are following now. So we're going to say the information for silver chloride, we know the number of mole of silver chloride. It's 0.0105 mole. Then because we want the mass, we can calculate the molar mass of this silver chloride. And to do that, we'll have to use our periodic table. So from the periodic table, we can look for the molar mass of silver. Silver is a molar mass of relative mass, atomic mass of 108, whereas chlorine is 35.5. So we're adding 108 and 35.5. So we're gonna go back to our equation and say right now, the molar mass of silver is 108, of chlorine is 35.5. So 108 plus 35.5 will give us the molar mass of, okay, guys, let me try to move this. The molar mass of 143.5 grams per mole. We want to know the mass. So we're going to say the mass equals to the molar mass. The mass, or the number of mole is the mass over the molar mass. Now we know we can cross multiply to get the mass. So the number of mole we know is 0.0105. Then we're going to multiply by the molar mass. Then the molar mass is 143.5. So we can now calculate the mass of silver chloride. So it's 0.0105 multiplied by 143.5. And this will give us if you're rounding to 2 decimal places, this would give us 1.51 gram. So this is the mass of silver chloride. This will be the mass of silver chloride. Then now, moving on to the next question. I believe, guys, you are following here. Okay, let me erase here and so that we continue. So if you don't understand, kindly pause the video and just try to analyze it on your own. Then you'll end up getting the answer. Okay. All right. Okay, then remember if they say, if we found that silver nitrate is the limiting, it means potassium chloride is in excess. It means it will not use all of its initial number of moles. Some will react, some will unreact or will remain. It will be in excess actually. All right, then now we can move on to the next question. Then the next question is still quantitative aspect of chemical change. It says Mary heats 50 grams of calcium carbonate. I apologize, guys. That react according to this reaction. Okay. Then now she collects the formed carbon dioxide gas. So it means that they're saying this is our gas. All right. Determine the number of moles of calcium carbonate. I think this one is straightforward. We know the information of calcium carbonate. We're given the mass. The mass of calcium carbonate is 50 grams. So it means you have to know the molar mass. And to know that calcium, let's use our periodic table. Calcium has a molar mass, relative atomic mass of 40. So what we're going to do is we're going to return to our question. And now let us substitute. So we know the molar mass of calcium is 40. Carbon we know is 12. And we have 3 atoms of oxygen. So we know the relative atomic mass of oxygen is 16. So this will give us 40 plus 12 plus 3 into 16. Then this will give us 100 grams. So this one will give us 100 grams per mole. Okay, then now we can say the number of mole is mass over the molar mass. So the number of mole of calcium carbonate will be, what is the mass? 50 over 100, and this will be 0.5 mole. So it's 50 over 100, which is 0.5 mole. I hope you understand. All right, then now we have answered the first one. Then the second one says she obtained only 18.6 grams of carbon dioxide gas. She obtained only 18.6 grams of this. Determine the percentage purity of calcium carbonate. Guys, how do we actually calculate the percentage purity? To determine the percentage purity, here is the formula which you need to know. Percentage purity is calculated by taking the pure sample, the pure mass of a sample. We take the pure mass of a sample, then we divide by the impure mass of a sample. So it's a pure mass divided by impure mass. So now, since now we want to know the percentage purity of calcium carbonate, it means this 50 grams is actually our impure sample. So now what we're going to do, we have to calculate the pure mass of this calcium carbonate. And to do that, we look on what we are given. We are given the information for carbon dioxide. Remember, carbon dioxide was produced, like it is produced from calcium carbonate. So with that, we are given the mass of carbon dioxide, which is produced. It's 18.2 grams. And we know the best way to relate two substances to use the number of mole, right, according to the stoichiometric calculation. Then now we're going to calculate the molar mass of carbon dioxide. This will be 12 plus 2 times 16. So this will be 12 plus 2 by 16. And this will be 44. So we're going to have 44 grams per mole. So we have to note the number of moles of carbon dioxide. The number of mole is mass over the molar mass, even if I do not write this. What is the mass? The mass is 18.2. The molar mass is 44. So we're going to say 18.2 divided by 44. It will give us a molar mass of 0. Let's round this to decimal places, 41 mole. So now we know the number of mole of carbon dioxide which was produced. Now, but we are not interested in the number of, we are not interested in the information of carbon, we're interested about the calcium carbonate, the pure calcium carbonate. So what we're gonna do is we're gonna compare calcium carbonate with the carbon dioxide according to the reaction. It shows that 1 mole of calcium carbonate produced 1 mole of carbon dioxide. So we're going to say 1:1. So what does it mean? It means if carbon dioxide used, we obtained 0.41 mole. So we want to know what is this. This one, if you cross multiply, it will still be 0.41. So it means now, what do we know? We know the information of calcium carbonate, the number of mole of calcium carbonate for a pure sample is 0.41 mole. And we want to know the mass because this is it's written in terms of mass. So we're going to say, we're going to calculate the molar mass of calcium carbonate. We know the molar mass of calcium carbonate. We have calculated it here. It's 100. So we're going to say the number of mole is mass over the molar mass. Now we want the mass, gonna cross multiply, then the mass will be the number of mole multiplied by the molar mass. So number of mole is 0.41, if I'm not mistaken, multiplied by 100. 0.41 multiplied by 100, that will give us 41 gram. So it means the 41 gram, it is the pure sample of that calcium carbonate. So it means to calculate the percentage purity, we're going to take a pure sample in terms of mass, then we divide by the impure, we multiply by 100. So what is the pure sample? A pure sample is 41 divided by 50, multiplied by 100, multiplied by 100. And what is the answer? So 41 divided by 50 multiplied by 100, this will give us 82%. This is our percentage purity. I believe you are following. I believe you are following. All right, now from here it says, sorry guys, I want to erase this so that we continue. Percentage purity. Remember, there is percentage purity and there's also what we call percentage yield. In terms of percentage yield, it means we take the actual yield, divide by the theoretical. Or in another book, they call it a calculated yield. Right. Then now, okay, let me check something. 50 divided by 100 is 0.5. So we can say 0.5. Another way is if we do not want to use mass to calculate the percentage purity, we can convert this to number of mole by saying we know this as a molar mass of 100. So we can say number of mole is 50. Oh, already we have calculated this. Its number of mole is 0.5. So we can say from that mole of 0.41, we divide by 0.5, then we multiply by 8. It was still going to give us 82%. So we can still use the number of mole instead of mass. Okay, all right. Then now, the other one is 6.2.3, it says calculate the mass of this carbon dioxide. Calculate the mass of carbon dioxide gas that Mary could collect if calcium carbonate was only 70% pure. If calcium carbonate was only 70% pure. So it means now they're just saying, what if we know the percentage of purity? It's actually they gave us the percentage to say, what if the percentage of purity was 70%? What would be the mass of this guy? So we're gonna say, okay, percentage purity is calculated by taking a pure sample in terms of mass divided by impure sample, then multiply by 100. Then what is our percentage there? Remember, in terms of if we were to multiply by 100, what is our percentage here? This would be, if we don't divide by 100, so we're going to say, okay, 70% equals to the pure sample divided by the impure. The impure already know it's 50 grams. So we can calculate the pure sample of calcium carbonate. I believe you're following. It will be 70 out of 100 multiplied by 50 grams. So we're going to calculate 70% of 50. So this will give us 35 grams. So it means the 35 grams is for calcium carbonate. And since we know for calcium carbonate, we want to know the mass of carbon dioxide. So we're going to say, okay, fine. For calcium carbonate, we know its mass, the pure sample of mass, it's 35 grams. Remember, 35 divided by 50, if you multiply by 100. 35 divided by 50. If you multiply that by 100, to give you 70%. So we can now determine the molar mass. We know the molar mass it's 100. We got that. So we can know the number of mole, which is mass over the molar mass. So it's 35 over 100. So this will give us the number of mole of 0.41. But since we don't want for calcium carbonate, we want for carbon, so we are comparing calcium carbonate and carbon dioxide with the ratio of 1:1. I hope you are following now. So now we know this has 0.35. Since it's 1:1, it means this one will also be 0.35 in terms of mole. Now we know the information for carbon dioxide. We know the number of mole is 0.35 mole. Then we can know the molar mass. Molar mass it's 44 grams per mole. We know this. Remember, it's 12 plus 2 times 16, which is 44. So it means you can say number of mole, it's mass over molar mass. We want the mass. So number of mole cross multiplication, mass is cross number of mole, it's 0.35 multiplied by 44. So 0.35 multiplied by 44, this will give us 15.4 grams. So it's no longer the same. I believe you are following. I believe you are following. All right, then the next one is the acid and base. I think this one will look at it in the second period after break. Yeah, let me just pause here, guys. And if there's any question, then you will keep in touch with me. Yeah, thank you very much for listening to me. See you after break. Okay.